Welcome to module 3 of chapter 8. In this module we are going to derive bounds on eigenvalues of subgraphs of a given graphs by using the eigenvalues of the graph X, and we also going to study eigenvalues of regular graphs and eigenvalues of strongly regular graphs. In module 3 of this chapter 8 we are going to study bounds on eigenvalues of subgraphs and eigenvalues of regular graphs. Objectives of this module are bounds on eigenvalues of a graph, eigenvalues of regular graphs and strongly regular graphs. To start with, recall eigenvalues of a graph, we mean that eigenvalues of this adjacency matrix of the graph X. The lemma is let Y be an induced subgraph of a graph X. Recall what is induced subgraph, earlier we defined. Then the minimum eigenvalue of a graph X is less than or equal to minimum eigenvalue of graph Y, where Y is induced subgraph of graph X, is less than or equal to maximum eigenvalue of graph Y, is less than or equal to maximum eigenvalue of graph X. That means the eigenvalues of Y are lies in between the eigenvalues of X, where lambda minimum of Z and lambda maximum of Z respectively denote the minimum and maximum eigenvalues of the graph Z. Let A of X and A of Y be adjacency matrices of the graph X and Y respectively. Then by permuting the vertices of X, we can write A of Y as upper left principal submatrix of A of X. Since Y is induced subgraph of graph X, it is possible to write the adjacency matrix of A or adjacency matrix of X as containing upper principal left submatrix as the adjacency matrix of Y and rest is remaining part. Let A be the unit vector of A of Y, that is adjacency matrix of graph Y, such that A into A is equal to lambda maximum of A. That means A is eigenvector corresponding to maximum eigenvalue of Y. And further we are also assuming that A is a unit eigenvector corresponding to maximum eigenvalue of Y. Let B be a unit vector in R of cardinality of V of X, that is number of vertices in X, obtained by adding zeros to the vector A. Then lambda maximum of Y is equal to A transpose into A of Y into A, which is equal to B transpose into A of X into B, which is less than or equal to, these two are equal, A transpose into A of Y into A is equal to B transpose into A of X into B. It is because B is appended from A by adding some zeros. So, that is why these two values are going to be equal. So, that is B transpose A of X into B now less than or equal to maximum of X transpose into A of X into X. This result we proved earlier. This is true for all symmetric matrices that we established earlier. So, this is less than or equal to maximum of X transpose into A of X into Y, that is equal to maximum eigenvalue of the graph X. Similarly, one can prove that lambda minimum of X is less than or equal to lambda minimum of Y. That means the minimum eigenvalue of X is less than or equal to minimal eigenvalue of the graph Y. Now we are going to study interlacing theorem. The next result is stated without proof. Let the eigenvalues of X be lambda 1 greater than or equal to lambda 2 and so on greater than or equal to lambda n. Let V be a vertex of X, and let eigenvalues of X minus V, that X minus V is a graph obtained by deleting vertex V from the graph X, be mu 1 greater than or equal to mu 2 greater than or equal and so on mu n minus 1. Then lambda 1 is greater than or equal to mu 1 is greater than or equal to lambda 2 and so on, mu n minus 1 is greater than or equal to lambda n. That means the eigenvalues of X minus V are lies in between the eigenvalues and in fact interlace between the eigenvalues of the graph X. Now we are going to give some bounds on the eigenvalues, but first we are going to show that the maximum eigenvalue of the graph X is lies in between the minimum degree of the graph X and the maximum degree of the graph X. Let X be any graph, then the minimum degree of the graph x is less than or equal to 2m by n, which is less than or equal to maximum value of the graph x and which is less than or equal to capital delta of x, where m is the number of edges and n is the number of vertices in the graph, and lambda max is the largest eigenvalue of the graph x. The proof: let A equal to A1, A2 and so on An transpose be a unit eigenvector corresponding to eigenvalue lambda max of A. Suppose Aj is an entry of A having largest absolute value. Note that without loss of generality, one can assume that Aj is positive, as we can take minus A in place of A as an eigenvector of lambda max. Hence, lambda max of Aj is equal to lambda max of A of j, which is equal to capital A into Aj, which is equal to summation Ai, where Vi comma Vj belongs to E is less than or equal to degree of Vj into Aj, which is less than or equal to maximum degree of x into Aj. Thus, the proof of one of the inequalities is over. Now, for the lower bound, we apply the following theorem. This we done earlier. Let A be a real symmetric matrix with eigenvalues lambda 1 greater than or equal to lambda 2 and so on lambda n. Then lambda 1 is equal to maximum of x transpose Ax with norm x equal to 1, and lambda n equal to minimum of x transpose Ax, where norm of x equal to 1, and lambda n is less than or equal to minimum of Ai less than or equal to maximum of Ai less than or equal to lambda 1. We will use this theorem. For that, we will apply this theorem to the unit vector and unit vector 1 by root n into E, where E is vector with all ones, column vector with all ones. To get lambda max is greater than or equal to E transpose by root n into A into E by root n, which is equal to 1 by n into E transpose into E, which is equal to 1 by n double summation Aij 2m by n, that is sum of all entries. Actually, we are dividing by n. Sum of all entries is equal to twice the number of edges. So, we are dividing by n. So, we have 2m by n. So, we proved that lambda max is greater than or equal to 2m by n, as sum of entries in the adjacency matrix is twice the number of edges. Now, we will give another bound for the maximum eigenvalue of the graph, that is here we are going to show that lambda 1 is less than or equal to 2m into n minus 1 by n power 1 by 2, where m is the number of edges and n is the number of vertices. Let x be a connected graph on n vertices, m edges. Let lambda max equal to lambda 1 greater than or equal to lambda 2 and so on lambda n be the eigenvalues of x. Then lambda 1 is less than or equal to 2m into n minus 1 by n whole power 1 by 2. So, we already seen that summation I is equal to 1 to n lambda I is equal to 0. The trace of A equal to 0 or sum of eigenvalues is 0. Similarly, trace of A square or sum of the eigenvalues of A square is twice the number of edges. Therefore, lambda 1 is equal to minus summation I is equal to 2 to n lambda I, as lambda 1 is greater than 0. So, we will get lambda 1 is equal to modulus of lambda 1, which is equal to modulus of summation I is equal to 2 to n lambda I, which is less than or equal to summation 2 to n modulus of lambda I. Now, applying Cauchy-Schwarz inequality to lambda 2, lambda 3 and so on lambda n and 1 1 1 1 unit with the vector E, we will get that 2m minus lambda 1 square is equal to summation I is equal to 2 to n lambda I square, which is greater than or equal to 1 by n minus 1 into summation n is equal to 2 to n lambda I whole square, which is greater than or equal to lambda 1 square by n minus 1, or equivalently 2m is greater than or equal to lambda 1 square into 1 plus 1 by n minus 1, which is equal to lambda 1 square into n by n minus 1. Hence, the required result follows. Graphs with the small eigenvalues. Since the largest eigenvalue of a connected graph is bounded from below by its average degree, one would expect that the graphs with small lambda 1 are rare and should have simple structure. So, let us consider few examples of connected graphs and n vertices. Lambda 1 is equal to 0, that is largest eigenvalue itself is 0 if and only if x equal to k 1. Lambda 1 is less than or equal to 1 if and only if x equal to k 2. Here note that we are assuming x is a connected graph. So, if values are less than or equal to 1 if and only if the graph has to be complete graph with the 2 vertices. If n is greater than or equal to 3, then the graph x contains a path of length 2 or k12. Hence, by interlacing theorem, lambda 1 is greater than or equal to root 2 and 1 less than or equal to lambda 1 is less than or equal to root 2 if and only if x equal to k12, as lambda max of k12 is equal to root 2. Now, we are going to see graphs with lambda 1 equal to 2. Lambda 1 is equal to 2 means all its eigenvalues are less than or equal to 2. There are many graphs with lambda 1 is equal to 2. The two copies of k12 join their middle vertices by a path of length n minus 5. This graph is going to give lambda 1 is equal to 2. The cyclic graph Cn for n greater than or equal to 3. The complete bipartite graph k14. The path on 5 vertices with path of length 2 attached to its middle vertex. A path on 7 vertices with an edge attached to its middle vertex. A path on 8 vertices with an edge attached to vertex at degree 2 from one of its end vertices. So, all those graphs which we discussed in the previous slide, that is 1 to 6, are called Smith graphs. It is straightforward to check that all these graphs have lambda 1 is equal to 2, the largest eigenvalue is equal to 2. As stated in the next theorem, they contain induced subgraphs of all graphs with lambda 1 less than or equal to 2. So, the theorem is the connected graphs with lambda 1 less than or equal to 2 are precisely connected induced subgraphs of Smith graphs. Now, we are going to study eigenvalues of regular graphs. Let x be a k regular graph, then k is an eigenvalue of x. If x is connected, then the multiplicity of k is 1. For any eigenvalue lambda of x, we have modulus of lambda is less than or equal to k. So, if x is a k regular graph, then we have k is an eigenvalue of x, and further if x is connected, k is a simple eigenvalue and all other eigenvalues modulus is less than or equal to k. Now, we will prove one by one. Proof of first part, that is easy. Let E is equal to 1 1 1, that all values, all vector with all ones, then it is easy to see that A is equal to K. Here it is very important, if you multiply to any matrix this vector E, means all ones vector, it is going to just sum of all the elements in the row. So, as we know that sum of elements in the row going to give the degree of that vertex. Since it is a k regular graph, the number of ones in any row is exactly equal to k. So, that is why it is easy to see that A is equal to k into E. Consequently, k is an eigenvalue with the corresponding eigenvector E. Let A is equal to A1, A2 and so on An transpose be an eigenvector of A corresponding to the eigenvalue k. Suppose Aj is the entry of A having largest absolute value. Without loss of generality, we will also assume that Aj is positive, as one can take minus A in place of A as an eigenvector of k. So, k into Aj is equal to A, capital A into vector A j, which is equal to summation Vi Vj belongs to E Ai, which is less than or equal to K Aj. As the vertex Vj is adjacent to exactly K vertices and Aj is greater than or equal to Ai for I is equal to 1 to n. Because of that, we got that K Aj is less than or equal to K Aj, but they are equal. So, that means that hence A is equal to Aj for all vertices that are adjacent to vertex Vj. Further, the condition that X is connected implies that we can recursively obtain A is equal to Aj for all I and j. Consequently, A is a multiple of E. Now, we will prove the part 3 of this result. Let AB is equal to lambda into B. As above, Bj is entry of B having largest eigenvalue, largest absolute value. Again, assume that Bj is positive. Then mod lambda into Bj is equal to modulus of lambda Bj, which is equal to AB at jth entry of AB, which is equal to modulus of Vi Vj belongs to E Bi, which is less than or equal to summation Vi Vj belongs to E modulus of Bi, which is less than or equal to K times modulus of Bj. So, we got that mod lambda is less than or equal to K. Now, by previous lemma, we have that if X is a connected K regular graph, then the minimal polynomial of X will be of the form X minus K into Q of X. Since K is an eigenvalue, so the minimal polynomial contains, for the minimal polynomial K is a one root. So, minimal polynomial is of the form X minus K into Q of X for some polynomial Q of X with integer entries, and Q of K is not equal to 0. Since if it is connected, K is a simple eigenvalue. So, now we use this idea in the next result, that is, let X be a connected K regular graph on n vertices, then the matrix J consists of all ones is equal to n by Q of K times Q of A, that is, J belongs to adjacency algebra of X, or J is a polynomial in X. The proof, let X is a K regular graph, its adjacency matrix A satisfies A into E is equal to Ke, where E is a column vector of all ones. Let X minus K into Q of X belongs to Z of X be the minimal polynomial of X, hence J A is equal to Aj equal to Kj. It is easy to prove that if a graph is regular, if and only if Ja is equal to Aj, that we not proved, but it is easy to show. Since A is the adjacency matrix of a regular graph, then each row has same number of ones. So, it is easy to show that a graph is regular if and only if Ja equal to Aj, and here it is K regular. So, Ja is equal to Aj is equal to K into J, and we have that Q of A into E is equal to Q of K into E. As we know that the eigenvectors of A and Q of A are same, let if you take the vectors as 1 by root n into E comma x2 and so on xn be orthonormal basis of R power n consisting eigenvectors of A with corresponding eigenvalues k, lambda 2 and so on lambda n. Thus, xi transpose into E equal to 0 for 2 less than or equal to I less than or equal to n. Hence, Jxi is equal to 0. Now, from equation 1 gives J into 1 by root n into E is equal to n by root n into E, which is equal to n by Q of K into Q of K into 1 by root n into E. So, this is equal to 1 by Q of K into Q of A into 1 by root n into E. As x minus K into Q of X is minimal polynomial of X, Q of lambda is equal to 0. So, Q of A into Xi is equal to Q lambda into Xi is equal to 0, that is n by Q of K into Q of A into Xi is equal to 0. Thus, we see that the image of two matrices J and n by q of k into q of k on the basis are same, hence two matrices are equal. Therefore, J is equal to n by q of k into q of a. Now, we are going to prove another lemma. Let x be a graph on n vertices. If J belongs to A of x, then x is a connected regular graph. With this, what we proved is a graph x is connected and regular if and only if J is a polynomial in A, the adjacency matrix of x. Let A be the adjacency matrix of A, then J belongs to A of x implies that J is equal to A naught I plus A1A and so on plus AR capital A power R, that is capital J is a polynomial, bold J is a polynomial in A for some positive integer R and AI belongs to R, 0 is less than or equal to I, less than or equal to R. As each entry of J is non-zero, for each pair ij there exists a smallest power of A, say t less than or equal to R, which has a non-zero entry. Hence, by definition, there is a walk of length t from vertex Vi to vertex Vj. Thus, x is connected. So, from the equation 3 we see that Aj equal to Ja. So, if dA equals degree of Vi, then so the degree matrix, that is d1, d2 and so on dn, if you take this is equal to Ja is equal to Aj is equal to d1, d2 and so on, d1, d1 first row is d1 and so on. So, thus we have dA is equal to dj for all I and j, hence x is a regular graph, hence the proof. This following observation gives the polynomial q of x explicitly. Observation: let x be a connected regular graph and k equal to lambda 1 greater than or equal to lambda 2 and so on greater than or equal to lambda n be the eigenvalues of x. We define h of x equal to n times product I is equal to 2 to n x minus lambda I by k minus lambda I. Then eigenvalues of h of a are h of k, h of lambda 2 and so on, h of lambda n, which is equal to n comma 0. Consequently, h of a minus j vanishes at all eigenvectors of a, or equivalently h of a is equal to j, which is equal to n by q of k into q of a. If x is a k regular graph, then we showed that k is an eigenvalue of a, where a is the adjacency matrix of the graph x. We also showed that every other eigenvalue of x is less than or equal to k. Further, we showed that if x is connected, k is a simple eigenvalue of the graph x. If j is matrix with every entry is 1, then x is regular if and only if ja is equal to aj, that means j commutes with a. Also, if x is connected graph, connected and regular if and only if j is a polynomial in a, that is the matrix J belongs to adjacency algebra of A if and only if the graph is both connected as well as regular. Now, we find the eigenvalues of x complement where x is a regular graph. Let x be a connected k regular graph on n vertices with eigenvalues k equal to lambda 1 greater than or equal to lambda 2 and so on greater than or equal to lambda n. Then the eigenvalues of x complement are n minus k minus 1, minus 1 minus lambda 2 and so on minus 1 minus lambda n. Let A be the adjacency matrix of the graph x, then adjacency matrix of x complement is equal to j minus I minus a. So, now using previous lemma, the matrices I, j and a have same set of eigenvectors. It is because we know that if x is regular, then j commutes with a and also I and a have same eigenvectors anyhow. So, the matrices I, j and a have same set of eigenvectors. So, U is orthogonal matrix formed using eigenvectors of A as columns, then UA U transpose is equal to diagonal of k lambda 2 the diagonal matrix with diagonal entries as k, lambda 2, lambda 3 and so on lambda n, and u A complement u transpose is equal to u times, since A complement, that is adjacency matrix of X complement is j minus I minus A into u transpose. So, which is equal to uj u transpose minus ui into u transpose minus ua u transpose. So, we are going to get diagonal matrix with entries n 0 0 0 and a diagonal matrix with entries 1 1 1 minus diagonal matrix with diagonal entries as k, lambda 2, lambda 3 and so on lambda n. So, we are going to get diagonal matrix with the diagonal entries as n minus k minus 1 minus lambda 2 and so on minus 1 minus lambda n. So, hence we got the required result. Now, as a corollary to this result, if X is a connected regular graph and X complement is also connected, if and only if adjacency algebra of X equal to adjacency algebra of X complement. That means both algebras are coincide when both X as well as X complement are connected. The proof is easy. Since X is connected and regular, so we proved earlier that J is a polynomial in the matrix A or J belongs to adjacency algebra of X. So, adjacency matrix of X complement is equal to J minus I minus A. So, that is also belongs to adjacency algebra of X. Hence, adjacency algebra of X complement is contained in adjacency algebra of A of X. Similarly, we can prove that adjacency algebra of X complement, adjacency algebra of A of X is contained in adjacency algebra of X complement. As X complement is n minus 1, k minus 1 regular connected graph. So, J belongs to adjacency algebra of X complement. Hence, A equal to J minus I minus adjacency matrix of X complement. So, this belongs to adjacency algebra of X complement. So, hence we proved that adjacency algebra of X contained in adjacency algebra of X complement, thus two sets are equal. Now, suppose that two sets are equal, then J belongs to adjacency algebra of X as well as adjacency algebra of X complement. Thus, by previous lemma X complement is connected and regular, hence we got the required result. Let X be a distance polynomial graph, then X is a connected regular graph. Recall that a graph is said to be distance polynomial graph if every distance matrix is a polynomial in X. For this, graph should be connected first. So, every distance polynomial graph is automatically connected. So, X is a distance polynomial graph, by definition X is connected. X has a diameter d, then by definition of the distance polynomial graph, the kth distance matrix is belongs to adjacency algebra or AK is polynomial in A. Consequently, this J is equal to summation all these distance matrices belongs to A of X. So, J is in the adjacency algebra of X. So, we have that X is a connected and regular. So, every distance polynomial graph is connected and regular, but converse is not true. It is nice to find an example. Now, we are going to define strongly regular graphs. A k regular graph X on n vertices is said to be strongly regular graph with parameters n, k, a, c if X is neither the complete graph nor the null graph. Any two adjacent vertices, say u comma u and v, have exactly a neighbors, and any two non adjacent vertices, say s and t, have exactly c neighbors. For example, C5, the cycle graph with 5 vertices, is a 5 2 0 1 strongly regular graph. That means, there 5 represents the number of vertices and 2 represents degree of the k regular graph. So, 2 regular graph, degree of the each vertex, and 0 represents the number of neighbors to adjacent vertices, and 1 represents number of neighbors to non adjacent vertices. Those numbers are fixed or same for any adjacent vertices or any non-adjacent vertices. Peterson graph is strongly regular graph with parameters 10, 3, 0, 1. A Paley graph on q equal to 4t plus 1 vertices is strongly regular with parameters 4t plus 1, 2t, 2 minus 1 and t. Recall that triangular graphs denoted line graphs of Kn, where the line graphs are the complete graphs, and it can be easily verified that they are strongly regular graphs with parameters n into n minus 1 by 2, 2 into n minus 2, n minus 2 comma 4. The line graphs of complete bipartite graphs, that is LG of KNN, are also strongly regular graphs with parameters n square 2 into n minus 1, n minus 2 and 2. There is a relationship among the parameters, that is, if you know 3 of them, then it is possible to find the 4th parameter. Let X be a strongly regular graph with parameters n, k, a, c. Let X is a vertex in X, then X has k neighbors and n minus k minus 1 non-neighbors. We will count the total number of edges between neighbors and non-neighbors of X in 2 different ways. Let V1, V2 and so on Vk be neighbors of X, then the number of common neighbors of X and Va is A, where I from 1 to k, hence the number of edges between the neighbors of X and non-common neighbors of X are k into k minus a minus 1. On the other hand, there are n minus k minus 1 vertices not adjacent to X, each of which adjacent to C neighbors of X. Hence, total number of edges between neighbors of X and non-common neighbors of X are C times n minus k minus 1. Hence, we have k times k minus a minus 1 is equal to C times n minus k minus 1. So, that is the relationship between the parameters n, k, a and c. Let A be the adjacency matrix of an n, k, a, c strongly regular graph, then we have A square is equal to k into identity matrix plus small a into capital A plus c times j minus I minus a. Recall that j minus I minus a is nothing but the adjacency matrix of the X complement. The eigenvalues of X are k and roots of the equation x square minus a minus c into x minus x k minus c is equal to 0. To prove the first part, note that the ijth entry of A square is the number of walks of length 2 from vertex I to vertex j. Moreover, this number is determined only by whether the vertices I and j are adjacent or non-adjacent or same. Thus, by definition of the graph X, we have A square ij equal to k whenever I equal to j, which is equal to A if I not equal to j but I and j are adjacent, is equal to say if I is equal to c if I not equal to j but I and j are non-adjacent, or equivalently A square equal to k into I plus small a into capital A plus c into A complement, which is equal to k I plus a into capital A plus c times j minus I minus a. Now, proof of second part. For second part, note that k is indeed an eigenvalue of X with an eigenvector E. It is because strongly regular graphs are already regular. So, here we are assuming it is a k regular graph, hence we have this. Now, let lambda is any eigenvalue of X corresponding to eigenvector X, then we have E transpose into X equal to 0. Hence, using the first part, A into lambda X is equal to A into capital A into X, which is equal to A square minus k I minus c into j minus I minus a into x, which is equal to lambda square x minus k x minus c times 0 minus 1 minus lambda into x. So, which is equal to lambda square plus c lambda minus k minus c into x. As x is not equal to 0, we must have lambda square minus a minus c into lambda minus k minus c equal to 0. Thus, lambda satisfies required equation. The following result characterizes connected regular graphs with 3 distinct eigenvalues. The proof is easy and left to is an exercise. It is given by Srikande and Bhagavan Das. Let X be a graph which is neither a complete graph nor a null graph. Then X is strongly regular if and only if A square is linear combination of matrices I and J and A, and X is strongly regular if and only if it has exactly 3 distinct eigenvalues. In this module, we studied important subclass of regular graphs called strongly regular graphs. One of the important result about strongly regular graphs is a connected regular graph is strongly regular if and only if it has 3 distinct eigenvalues. With this, we end this module.